Welcome everyone. Today's lecture focuses on two widely used machine learning approaches, k-nearest neighbors, KN, and regression models. We'll learn how these methods are applied to predict house prices, a classic yet highly practical problem in data science. Whether you're new to these concepts or looking to deepen your understanding, this session has something for everyone. In this chapter, we'll set the stage by exploring the fundamentals of case neighbors, KNN, and regression models. These algorithms form the backbone of many predictive tasks in machine learning. By understanding their principles, you'll gain insights into when and why to use each, depending on the problem at hand. KM provides a direct approach to predictions by focusing on proximity. Picture it like gathering opinions from your closest friends when making a decision. KN evaluates the closest data points to form its prediction. Think of it as simple, yet surprisingly effective for certain datasets. Now, let's dive into the backbone of KNN. Consider how it leverages proximity by calculating distances. We'll discuss the importance of hyperparameters like the number of neighbors and the choice of distance metric, which can significantly influence the outcome. Let's uncover what makes KNN tick. KNN operates on the principle of similarity, essentially finding the data points closest to a given input and using them to make predictions. Imagine you're trying to decide how popular a coffee shop in your neighborhood is. If 5 nearby stores are bustling, you predict this one is popular too. That is KN in action. It's crucial, however, to carefully choose the distance metric and number of neighbors, key to balance between capturing nuanced patterns and avoiding overfitting. Let's break down these distance formulas that are vital for KNN. The other Euclidean distance is great for continuous data. It calculates the direct straight line distance, which is intuitive in low-dimensional spaces. The S-Manhattan distance, on the other hand, sums absolute differences between point coordinates. This is particularly useful in high-dimensional datasets with sparse features or grid, like layouts in Node G, city street distances. Lastly, the Minkowski distance is a flexible generalization that enables experimentation by adjusting the parameter ZPT. Real-world tip always test how different metrics influence KN results. The beauty of KN lies in its simplicity. It doesn't perform any explicit training, but instead looks up similar instances at prediction time. However, this simplicity comes at a cost. KN is computationally expensive as the dataset grows and is also highly sensitive to unscaled features. For example, if one feature, say like income, has larger numeric ranges than others, like age, it will dominate the distance computations unless properly scaled. Finally, be mindful of your key value. Start with an odd number to avoid ties in classification and use cross-validation to tune it effectively. Balance is the key here. Selecting the right value of k is like finding the perfect Goldilocks zone for your model. A small key, e.g. 1 or 3D, may capture noise in the data, especially if there are outliers. Imagine deciding a neighborhood's average income based on just one house. On the other hand, a very large k, e.g. 50, dilutes local patterns, resulting in overly generic predictions. Always tuned by testing, ideally with cross-validation. For instance, you might split your dataset into folds and systematically validate how different k values perform to find the sweet spot between overfitting and underfitting. Deciding on the right distance metric is crucial for the success of a KNN model. Euclidean distance works well for low-dimensional continuous data, whereas Manhattan distance can handle high-dimensional or sparse datasets effectively. Minkowski offers a middle ground by allowing you to customize the metric through the RP parameter. Always consider the type of features in your dataset, and remember, experimentation might be needed to find the optimal distance metric for your specific scenario. Preprocessing, specifically feature scaling, is an indispensable step for KNN. For example, if one feature like income ranges in thousands, while another feature like the number of rooms ranges only in tens, the larger scale feature will overpower distance metrics. Using tools like standard scaler or min-max scaler ensures a more balanced contribution from each feature, allowing KNN to perform optimally. Always remember to apply the same transformation to both training and testing datasets to avoid data leakage. This code snippet demonstrates how to implement feature scaling using standard scaler from Scikit-learn. First, we fit the scaler on the training data to learn its mean and variance. Then we apply this scaling to both the training and test datasets. Remember that the test set should only be transformed using the parameters derived from the training set to prevent introducing bias or data leaks. While KNN is simple and intuitive, there are several drawbacks. It struggles with very high dimensional data to the curse of dimensionality, which dilutes the meaning of distances. Additionally, its computational cost can grow exponentially with larger datasets, as it involves calculating distances to every training point during prediction. These challenges make it critical to preprocess data effectively and possibly limit KNN's application to smaller, well-structured problems. When working with KNN, understanding its limitations is crucial. The curse of dimensionality means that as we add more features, the data points become equidistant, making it harder to distinguish neighbors effectively. Similarly, the computational cost of running KNN increases linearly with the size of the dataset, which can become impractical for massive data. Another key challenge is its sensitivity to feature scaling. If features have drastically different scales, e.g. income in thousands vs. dimensions in meters, the algorithm's performance can break down entirely. We'll later discuss techniques like dimensionality reduction and scaling to minimize these issues. Although KNN has its challenges, there are well-established strategies for improving its performance. Reducing the dataset's complexity with dimensionality reduction methods like PCA can make the algorithm faster while maintaining accuracy. Additionally, using advanced data structures like KD trees or ball trees helps speed up the neighbor search process, especially in moderate dimensional data scenarios. Most importantly, scaling features correctly using standardization or normalization is a non-negotiable requirement for ensuring meaningful distance computations. Finally, consider sampling or stratified reduction methods for very large datasets to make computation feasible without sacrificing model quality. In this section, we'll pivot from KNN to explore regression models, which are pivotal in predicting continuous outcomes. We'll examine linear regression models like simple and multiple regression, which are foundational, and contrast them with non-linear models such as gradient boosting that handle more complex relationships. Understanding when to use each approach is key to mastering predictive modeling. Regression models are instrumental in making predictions where the target variable is continuous, such as predicting stock prices, house values, or temperatures. Linear models work well when the relationship is straightforward and primarily additive. But when the data exhibits more intricate patterns, linear assumptions fall short and non-linear models come into play. Gradient boosting, for instance, can iteratively refine predictions by learning from previously missed trends. As we explore these approaches, think about the trade-offs. Linear models are interpretable and efficient, while non-linear models excel with complex datasets but often require more tuning. Linear and non-linear regression models offer two distinct approaches for capturing relationships in data. Think of linear models like drawing a straight line through the data points, a simple, easy, to interpret solution when relationships are straightforward. Non-linear models are like fitting curves, capturing complexities linear models can't. We'll explore when to use each strategy, focusing on what your dataset demands. Now, let's turn to real-world data. The California housing dataset. It's a widely used dataset for regression problems, particularly predicting house prices. We'll analyze its features, examine its structure, and understand why it's perfect for testing models like KNN and regression. Stay tuned. This dataset offers a mix of simplicity and depth. Let me provide a quick overview of the California housing dataset. It originates from the 1990 US Census and is often used for testing regression models. The predictor features include economic aspects like income, housing characteristics like the number of rooms, and geographical details like latitude and longitude. This diversity helps us study how different variables contribute to housing prices. Here's a breakdown of the dataset's features. You'll notice it's a mix of socio-economic and spatial metrics, such as median income and geographic coordinates. Each feature gives us unique insights. It's this variety that makes the dataset ideal for regression analysis. For example, latitude and longitude can reveal spatially driven price patterns. This dataset contains 6040 instances including 8 predictors and a target variable representing median house value. Importantly, there are no missing values, which ensures efficient preprocessing. Notice how attributes like income and room count have a wide range. This provides excellent material for exploring advanced predictive models. The geographical features, latitude and longitude, are key to uncovering hidden regional trends in house prices. For instance, we can analyze coastal or urban areas which often show higher demand and prices. Visualizing housing locations geographically will reveal these correlations vividly, aiding better model interpretation. Here's the Python code to load the California housing dataset using fetch California housing from Scikit-learn. Note the use of the sFrameTrue parameter. This automatically converts the dataset into a pandas data frame. This makes it intuitive to manipulate and explore the data. The DESCR attribute also provides a concise dataset summary. The California housing dataset provides socio-economic and housing-related insights drawn from the 1990 US Census. Its target variable is the median house value in the 100,000s. Key features include income, house age, and population data, alongside geographical indicators like latitude and longitude. Together, they present a comprehensive foundation for modeling and prediction tasks. This scatter plot highlights the correlation between median income and house prices. Notice the clear trend: higher incomes tend to correspond with higher house prices. However, there are a few outliers where low income groups still have higher house values, perhaps indicating unique locations or markets. Pay attention to the gradient in distribution as it provides valuable insights for model development. This map, like scatter plot, visualizes the geographical distribution of house prices across California. Areas closer to coastal regions and urban centers, such as Los Angeles and San Francisco, show higher house prices. Note how longitude and latitude are essential features for capturing spatial patterns in housing data. This visualization underscores the importance of integrating geographical information in regression models for better accuracy. In this chapter, we will focus on data preprocessing, a crucial step before feeding data into machine learning models. Proper processing ensures the model interprets data accurately and prevents errors. Think of it as preparing ingredients before cooking. If you skip it, the end result may not turn out well. Preprocessing involves loading the dataset, converting it into a manageable format like a pandas data frame, and exploring it for any anomalies. A key step is splitting the dataset into training and testing sets to prevent overfitting and validate model performance on unseen data. Keep these steps in mind whenever working on real-world machine learning problems. Here we are converting the California housing dataset into a user-friendly pandas data frame format. This allows us to easily explore, manipulate, and analyze the dataset using various built-in pandas functionalities. Notice that we also add the target variable, a price, as a new column at the end of the data frame for convenience. A quick check for missing values ensures our data preprocessing pipeline remains robust. If we find any missing values, we will need to handle them through techniques such as imputation or removal. Fortunately, the California housing dataset does not contain any missing values, which saves us an extra step. This code snippet prints the count of missing values for each column in the dataset. Ideally, all columns should show due missing values, confirming that the data is clean and ready for further steps. Getting a high-level overview of your dataset is essential. With Describe, we can uncover distribution properties, detect anomalies, and understand the range of values for each feature. This step also provides insight into scale differences between features, helping us identify if feature scaling is required. Here, we use the describe function to calculate basic statistical metrics for each feature in the dataset. These include measures like mean, standard deviation, minimum, maximum, and the quartiles. It's a quick way to gain a high-level understanding of the data distribution and spot any anomalies, such as extreme outliers or missing values. Now, let's talk about splitting the dataset into training and testing subsets. This is a key step in machine learning pipelines to ensure that our model generalizes well to unseen data. By using separate datasets for training and evaluation, we can effectively measure how our model is likely to perform on real-world data. Splitting the dataset is critical to avoid overfitting, a common problem where the model performs excellently on the training data but poorly on new data. The most common split is 80% for training and 20% for testing, though this ratio can vary depending on the dataset size and application. Here, we use the train test, the split function from Scikit-learn to split the dataset. We set test size 0.2, which reserves 20% of the data for testing. The randomness stated 2 ensures that we get reproducible results every time the code is run. This is important for consistent experimentation and debugging. When performing machine learning tasks, splitting your dataset into training and testing sets is essential to evaluate model generalization. Here, we've assigned 80% of the available data to the training set for training the models, while 20% serves as the test set to evaluate performance on unseen data. Using a random seed ensures consistent results if the split is repeated. A systematic split like this prevents data leakage while providing a reliable benchmark for model evaluation. Remember, these are standard proportions, but they could vary for imbalanced datasets or specific requirements. Exploratory data analysis (EDA) is a crucial phase of any data science project. Here, you aim to uncover patterns, relationships, or anomalies in the dataset. By visualizing and summarizing key features, you gain an intuitive understanding of the data before diving into pre-processing or modeling. This step ensures that you detect critical issues like missing values or outliers and identify trends that could influence your modeling approach. EDA lays the groundwork for better decision making in later stages. For instance, if we observe skewed distributions or outliers during this step, we might decide to transform data or exclude certain observations. Moreover, identifying correlations between input variables and the target variable can guide feature selection. Through this process, we prepare not just the dataset, but also a logical strategy for the problem at hand. This code generates a pair plot using the Seaborn library, visualizing scatter plots of feature combinations along with kernel density estimates (KD) on the diagonal. By focusing on key variables like Medding S median income, avrooms S average rooms, and Housing we can assess their relationships with housing prices, a price, expect to observe positive or negative trends, and potentially identify correlations. For example, you may find that higher median income is usually associated with higher house prices. A useful insight as we proceed to modeling. Let's break this down. When income rises, so do house prices. No surprise there. What's interesting is the non-linear link between average rooms and price. While more rooms generally mean higher prices, adding too many rooms seems to have diminishing returns, possibly due to luxury real estate skewing the results. Don't miss the few extreme outliers in the data that might require cleaning or alternative modeling. This heat map reveals how strongly each feature is correlated with the others. Pay close attention to its medias. It has a strong positive correlation with price, confirming income as a key driver of housing values. You also notice weaker or even negative correlations, such as latitude and longitude with house prices, reminding us how geographical location impacts affordability. Correlations tell a story. Income drives housing prices most effectively, while room counts add little explanatory power. Geographical features showing negative correlations make sense when you consider real-world geography. Prime locations along the coast are pricier, but as you move inland, costs fall. Be cautious about interpreting weakly correlated features. They may not add much to our final model. This visualization paints a clear picture. Higher median incomes translate to higher house prices. Notice the linear and slightly upward trend with some interesting clusters of data, but also watch for exceptions. Wealthy areas with unusually low prices may suggest unique regional phenomena or errors in the dataset. Scatter plots like this are invaluable in detecting patterns and preparing our data for regression models. It's intuitive to associate higher incomes with higher property values, as areas with wealthier populations typically have greater demand for housing and amenities. However, the dataset reveals some compelling exceptions: low-income regions with high property prices. These could be due to factors like exclusive neighborhoods, prime locations, or historical significance. As analysts, such patterns should prompt further investigation into localized influences. Now that we've prepared and explored the dataset, it's time to dive into model training. We'll experiment with two different types of models: K-nearest neighbors, K-in and XGBregressor. These models allow us to analyze the data at both ends of the spectrum: KNM for its simplicity and XGBregressor for its advanced scalability and performance potential. Let's first explore k-nearest neighbors, a foundational algorithm for regression. While often used for classification, KNN regression predicts a continuous target variable by averaging the values of the key closest data points. It's simple to understand, making it an excellent starting point for beginners, though it does come with unique challenges and limitations. KNN is straightforward but relies heavily on how we prepare the data. For regression, it predicts by averaging values of k nearest neighbors according to a chosen distance metric. The choice of k and the scaling of data significantly affect its performance. While simple, KNN can struggle with larger datasets or high-dimensional spaces due to computational inefficiencies. This snippet shows how to train a k-nearest neighbors regression model using Scikit-learn. The parameter and the neighbors is set to 5, meaning the model will use the 5 closest neighbors to make its predictions. Always ensure the data is properly scaled, as KNN is highly sensitive to the range of feature values. The KM model achieves decent performance, but its limitations are apparent. R squared indicates the proportion of variance explained, which here suggests room for improvement. The MA score is reasonable for a regression task, but not overly precise. Remember, feature scaling and techniques like dimensionality reduction, e.g., PCA, can significantly improve KNN's performance. Now, we transition to a more powerful regression method, the XGBoost regressor. This model addresses many limitations of simpler models like KM by efficiently handling high dimensional data and providing better interpretability through feature importance analysis. XGBoost is a state-of-the-art algorithm in the world of regression. It balances flexibility and efficiency, making it a go-to choice for many machine learning practitioners. Crucially, it can handle large datasets and complex feature interactions and provides tools to easily interpret model behavior through feature importance charts. Here we're training the XD regressor model, a powerful gradient boosting algorithm suitable for regression tasks. The eval the metricgrams explicitly specifies that the model will evaluate root mean squared error during training for better interpretability. The random state ensures reproducibility. Remember that additional hyperparameter tuning may significantly enhance the model's performance. In this step, we evaluate the training performance of the XGB regressor. The R-squared score, R2, measures how well the model explains the variance in the data, while the mean absolute error, SEMAE, quantifies average prediction error. These metrics help gauge whether the model is underfitting or overfitting on the training data. The training results reveal that the XDB regressor performs exceptionally well on the training dataset. An ARTA value of 0.94 suggests a strong correlation between the predicted and actual house prices, while the low MA indicates minimal average prediction error. As we proceed, we will assess whether these strong results generalize to unseen test data. We will now move on to evaluating the model's predictions on the test dataset. This step is crucial in understanding how well the XGB regressor generalizes to unseen data. We'll compare the predicted and actual house prices for various evaluation metrics. This plot compares the actual house prices with the predicted prices for both the KN model and the XGB regressor model. The dashed black line represents the ideal scenario where actual equals predicted. Notice how XGB regressor predictions align more closely with the perfect fit line, indicating better performance, while KNN predictions display greater dispersion. This visual reinforces the numerical evaluation metrics and shows why XT regressor is better suited for the dataset. When comparing performance metrics, it's clear that XGB regressor outperforms KN on test data. The higher R squared value of 0.84 reflects the strength of the XGB model in capturing the variability in house prices. Additionally, the lower MEME of 0.30 indicates that XGB regressor makes smaller prediction errors on average compared to KNN. This reiterates the importance of using sophisticated models like XGB for datasets with non-linear and complex patterns. In this concluding section, we summarize the critical lessons from our analysis and experimentations while paving the way for future explorations. It's important not only to evaluate the immediate results, but also to reflect on how we can extend and improve upon these methods. Here's what we've learned: KNN, while easy to understand and implement, is less suitable for datasets with high dimensional features and large variability. Its performance heavily depends on preprocessing like feature scaling, but even with optimization, it's outperformed by the XGB regressor, which excels in capturing intricate data patterns. This emphasizes the importance of selecting the right model for a given dataset and investing time in preprocessing steps. We are not done yet. The results so far demonstrate the potential for improvement. For instance, tuning hyperparameters could further boost the performance of XGB regressor or KNN. Additionally, we could explore alternatives like neural networks or random forests to benchmark against XGB. Lastly, domain-specific feature engineering could bring new perspectives, such as creating custom zones using latitude and longitude. Our next step could also involve deploying the model into a real-world scenario. Let's embrace these challenges as opportunities to build even better models. For our next steps, we'll refine and extend what we've learned. First, optimizing hyperparameters, especially for complex models like XGB regressor, can significantly boost performance. Additionally, testing alternatives like random forests or support vector regressors is crucial, as different models may better capture specific patterns in your data. Also, don't underestimate the power of feature engineering. Try adding interaction terms or transforming existing features to unearth new predictive insight. Finally, employing techniques like cross-validation adds robustness to our evaluations, and using ensemble methods can further increase predictive power by leveraging the strengths of multiple models. Let me leave you with some resources to deepen your understanding. These references provide comprehensive guides on tools, libraries, and datasets used in today's analysis. Make sure to explore these links to solidify what you've learned and discover advanced content for future projects. The links provided here serve as your go-to resources. The Scikit-learn website gives a complete walkthrough for machine learning with practical examples and tools for data preprocessing and evaluation. If you're working on gradient boosting models, XGBoost documentation is a goldmine for advanced features and techniques. Lastly, if you want to experiment further or replicate the analysis from today's session, the California housing dataset is an excellent starting point. These links will help you stay equipped for deeper experiments and future projects.